Okay, let's do another example. So here we now have a distributed load acting over a beam that's supported by another beam, CD, by a link CD, pin at A, and we're asked to find the normal shear and bending moment at B, which is at this location right here in the middle. So we'll say that's right there in the center. One important thing to notice right away is that CD is a two-force member. AC is not, because we have that extra distributed load, but CD only has loads acting at pins C and D, and so therefore we know its line of action. So again, let's go ahead and draw the free body diagram for this member and solve for the reactions. So we'll start first with the free body diagram of member AC and see what we get. So you can pause and try and do it on your own, or you can follow along. So at point A, we have a pin, so we know we have an AY and AX. At point C, we know we have force CD. And we know, for example, FCD is on a 3, 4, 5 triangle, right? By definition, with the geometry given in the problem. And now we're going to go ahead and reduce that distributed load just to one single equivalent force. So we have 50 pounds per feet up here times 8 feet of load as a constant, right? So now we have 400 pounds acting right in the middle, right at that point B that we're asked about. All right, I'm just gonna write here. I did the math offline. So pause, do the math, make sure you get these numbers. If we do sum of moments at A, you should be able to get FCD right away, equal to 333 and a third pound. And from sum of forces X, then we can get AX equal to minus 266.7 pounds. And then finally, sum of moments at C at the very end will get us AY equal to 200 pounds. Okay, so FCD is magnitude only, right? We can decompose it into components later if we want to. So now what's our next step? We need to go ahead and actually create the section. So we'll make our little squiggly line and separate our free body diagram actually into two separate sections. So here, take this thing and split it up here. And from there, we want to go ahead and draw free body diagrams and try and find the easiest one that's going to get us what those internal forces are where that squiggly line is. So we'll select the easiest free body diagram. So let's think about what those are going to look like. So from the left-hand side, I have my forces, AY, AX. Now I just have half of the distributed load, right? And that's still going to act in the middle. So here's my distributed load. On the right-hand side, I still have the distributed load. And then I have force CD, right? So I can go ahead and simplify the distributed loads on either one into their equivalent forces. So I haven't finished this completely. Just make a copy here. It's the wonder of technology. And now I actually have 200 newtons here. And then on the right-hand side, same thing. I can simplify this again and say now I just have 200 newtons right here. And of course, on either side, I still have, just scooch that over a little. I have the internal forces to consider, right? So these are not complete yet. So normal force pointing out, shear force directing a clockwise rotation, and then a concave moment. And the same would be true on the left-hand side. Normal, shear pointing up now because I'm on the left side, and then a moment. And so really it's up to you to decide which one you think looks a bit easier. I kind of like the one on the left only because AX and AY are in their Cartesian components, and I don't have to worry about any errors with sines or cosines or not using the 3, 4, 5 triangle correctly. So let's go with this one and set up our equations of equilibrium. We know sum of forces X. Now we have N plus AX equals 0. Sum of forces Y, AY minus 200 newtons minus V equals 0. And sum of moments at A, again, how far are we? I think it's 4 feet. Yep. So we need some geometry here to help. So taking our sum of moments at A, the 200 is going to generate a clockwise spin, which will be negative, therefore, 200 newtons. And that has a moment arm of 2 feet. Oh, sorry, pounds. I just realized these are pounds because 50 pounds per feet. Sorry about that. I could go back and edit this, but we'll just stick with it. All right, 200 pounds plus the shear is still going to contribute, and that's also generating clockwise spin, so that's minus V times 4 feet. And then plus M, which is in the positive counterclockwise direction. And so you can see here that with all of these, you can solve for N, you can solve for the shear, and then you can finally solve for M, right? And that's the way to determine what the internal forces are at B.